Okay, let me continue with the third question. Let me share my screen. Question 3 says water is flowing at a velocity of 8 meters per second and a depth of 2.5 meter in a rectangular channel of 4 meter wide. You can see here. It has three parts. Part A, if there is a smooth expansion in width to 5 meter, like in this image, at the downstream, determine the depth of water in the expanded section. So it's actually asking us what is the depth of flow here, or Y2, we can say. To start with, we can calculate the discharge easily because we know the velocity at section 1, we know the channel width, and we know the depth. So basically, velocity times width times depth, because width times depth gives us the cross-section area, because it's a rectangular channel. And so it's 8 times 4 times 2.5, it is 8 meter cube per second. Of course, discharge will be constant through this channel. It will be 80 meter cube per second, but the small q will change because the channel width is changing. If we knew the velocity at this section, for example, we could say since the energy at this point and at this point will be equal, we could calculate the depth easily. But since we don't know the velocity here, we need to follow a different solution method. For this solution method, we need to calculate small q for section 1 and section 2. For section 1, it is basically discharge divided by the channel width. So 80 divided 4, it is 20. Here, same 80 divided by 5 this time, because the channel width is 5 meters. It is 16 meters per second per meter. We are calculating y critical 1 and y critical 2, and we know what is the y critical formula. Small q squared divided by g into the cube root. So 20 squared divided by 9.81, it is 3.442 meters, and for the section 2, it is 2.966 meters. As I said, energy at section 1 and section 2 are equal. Since we know the velocity and the flow depth at section 1, we can calculate the energy at section 1 easily. What is energy? Flow depth plus v squared over 2g, so 2.5 plus 8 squared divided by 2 times 9.81, it is 5.762 meters. Now we will equate this to the energy at section 2, and we will find the y2, but instead of velocity, as I did in the first question, I guess, I will replace this velocity instead of discharge divided by cross-section area, and instead of discharge, we are writing small q times b. Then b's are canceling each other from coming from cross-section area and this small q times b. At the end, we will left with y2 plus small q squared divided by 2g y squared. It was equal to 5.72 meters, 762 meters. And from here, you can get y2 as 1.82 meters. This was the part A. Now, in the part B, it says find the maximum allowable smooth contraction in width without any choking. So it's basically asking us how much we can contract this channel without experiencing any choking. So if we want to find our maximum allowable contraction, this channel width must be the smallest. So this is why we call it B minimum. And if B is minimum, the small q should be maximum. This is why I wrote these two. So if we are dealing with the minimums, that means we are in the critical situation. Therefore, we can calculate the energy by using a critical equation, critical depth equation. We calculate this energy. We already calculated here. It was 5.762 meters. Once we equate it to from the critical energy equation to 3.3 divided by 2 y critical, we can find the y critical. Y critical is 3.841 meters. Once we find the y critical for this section, then we can calculate the small q for that section, because y critical is equal to q squared divided by g inside of a cube root. So from here, if you take this q outside of the equation and leave it alone, you'll get this term. So what is it? Inside of a square root, g times y critical cube. So what is g? 9.81. What is y critical? It was 3.841 meters. And we find q max as 23.58 meter cube per second per meter. We know discharge was 80. We found our q max. Now we can easily calculate our b minimum. So 80 divided by this q value, it will be equal to the 3.393 meters. So if we choose our channel width something more than our b minimum, there will be no choking. If we select it less than this b minimum, less than the standard, there will be a choking. This was the part B. And lastly, in part C, it says if the width is contracted to the 3 meters, which is less than our minimum, what is the minimum amount by which the bed must be lowered for the upstream flow to be possible as specified? So question is basically saying if this width is contracted to the 3 meters, as I said, which is less than our B minimum, so we are going to experience the choking, but it says how much this flow channel bed should be lowered so that we won't experience choking. So it's basically asking us delta Z minimum. So how can we start? We can start writing in our energy equation for section 2. What is it? Y2 plus Q squared divided by 2GY squared. From here, we can calculate our Q from here. Why? Because we know our channel width. It is 3 meters. We know discharge. It is 80 meter cube per second. And our Q is 26.67 meter cube per second per meter. And if we put this Q into this equation, later we can calculate it. Y critical for the energy, actually, we can also use Y critical because we don't know what is the flow depth here. And since, again, we are dealing with the minimums, we can use critical energy equations instead of using this equation to calculate energy. What is Y critical? As always, it is Q squared divided by G inside of a cube root. We found our Q, it was 26.67 meter cube per second per meter. G is 9.81, so Y critical is 4.17. If we knew the flow depth, we could use this equation. But since we don't know, we can also use this one. Basically, what is energy? It is energy at section 2. It's equal to energy minimum, and it is 3.3 divided by 2 Y critical. So what was Y critical? 4.17. So energy at section 2 is equal to 6.25 meters. if we look at this side view, the cross section, we can write the energy equation between section 1 and section 2, and we can calculate this delta Z minimum. What is the energy equation? So energy at section 1 plus this downward step, which is delta Z, will be equal to the energy at section 2. We calculated the energy at section 2 from critical energy equation, which was 6.25. We calculated energy at section 1 in the part A already. It was, find it, 5.762. It is still same because we didn't change anything about section 1, so it is still same. And then from here, we can calculate delta Z, which is 0.488 meters. And this is the end of question 3. After a small break, I will continue with the last question, which is an old exam question.